So I shared in the chat the notes for today, and I'll be guiding you in this topic of deep learning. And this is a very wide and broad topic. So I'm showing right now a picture, the whole picture, so you can try to see where you are positioned. For example, if you're working on the natural sciences or the health sciences or even social sciences, um, this is the range of the data science. And when we talk about machine learning is an intersection between data science and artificial intelligence from computer science. And also you have that other sciences like cognitive science and also robotics. They have to do with AI. And you have heard about large language models, for example, ChatGPT, which is part of AI, but also part of data science. And also in data science, we have some intersection with statistics and mathematics, data systems, high performance computing, and also sensors and the Internet of Things. So let me go deep. So when we're talking about deep learning is just a subset of machine learning, and machine learning is a subset of artificial intelligence. So when we're talking about deep learning, you have seen so many applications today of deep learning, like large language models, and also all these autonomous vehicles, computer vision, all these generative AI is part of deep learning. Okay, so deep learning starts with the simple trying to reproduce how we think, and we start initially trying to mimic how biology works with all these axons, and you have all these perceptrons. So you have receiving the signals, the biological systems, they receive their signals and then they shoot some actions through these connections. So the signal travels from one dendrite to the axons. In a similar way, in deep learning, we have this input information into some entity, and this entity will produce some output. And when we have several of these, we may have like an input layer, and then we have all the information going into the next level, to the next layer, which is called the hidden layer, and that the output from that layer can go to a third layer, and then at the end will be some output, similar as the axons work in biology. Okay. Now, in this workshop and other workshops, we have been talking about classical machine learning, and also there is a special workshop on deep learning. So what is the difference between machine learning and deep learning? So on the left, we have what is classical machine learning. So we have some problem that you want to address, and then we have the data. The data is then sent into an algorithm. The algorithm will reprocess the data, and then we are validating and iterating, and then we train our model until we have some output from the model, and we validate that model. So this took some training process, and in the training process, we have to do something in order to improve the precision of our algorithm. So that's classical machine learning. On the other side, deep learning. On the deep learning, we have the algorithm, and then this algorithm will just take all the input data, which can be raw data. The algorithm by itself will try to learn if there are some patterns hidden in the data, and then it will produce some output. So in deep learning, we don't have any interaction with the algorithm. We just give the data, and then by itself, it will produce the output. Okay. So these are some of the basic topics in deep learning. We have the perceptron model, which was mimicking the biological perceptrons and neurons. Then we have the multi-layer perceptron. Also, we have the convolutional neural networks, the recurrent neural networks. We also have these transformers, and lately everyone is talking about transformer and large language models. And you can see the definition of each topic. But so I'm trying to focus on what is a neural network, artificial neural network. And we will see, we will start with a single layer neural network where we have some input values and it has probably some bias, and then we will add some weight coefficients, and then this will produce some output. There's going to be an activation function, and then we are trying to predict something. And mathematically, you can write this as a linear equation, which is just a combination of different variables, x1, x2, until xm, and we have some weights, w0 up to wm, and then this sum of this linear equation can be synthesized as a sum in mathematical terms of these products of the weights times the variable x plus some bias, and that will give you some prediction. And vectorially, you can write this equation as simple as this one. So if you're following the talk, let me open this link, and I will ask you to open it also, and we'll try to play with this model. No, I didn't get the right one. Try again. Okay, try again. So can you open that example, please, and tell me if you're there? So this example will show us how a neural network works. So we have several inputs. We may have some weights, and then there is some bias, and at the end, we will have some output. And there is an example here where we have this model where we have some input, and then we have some weight, and there's some output. So this is the form of the mathematical equation. So usually when we have several experimental points, then we will try to fit some line that minimizes the error of these measurements. And this line will be our theoretical model. And there are many lines that can pass near the 3 points here, but there will be only one line that optimizes the sum of the squares or the difference of the distance of the points to the theoretical line. Okay, and this line will have some slope, and also it will have some intersection point. Okay, so we will try to predict this line, and this prediction will have some error, and the idea is to try to minimize the error. So we will do it by hand. So let's try to play with this example over here. So we have 3 points. We have a line, and there is some error here. The error will be just the sum of the squares of the differences between the blue points and the red dots. And the red line is just the theoretical line. And this red line can predict, for example, what will be the corresponding value for at 1,000. And then we just follow the line. It will be around 250 or so. So this is the line and has some error. We can play with the weight. The weight will be just the slope of the line, okay? And we can play with the bias. The bias is just the intersection point with the x equals 0 axis, okay? So the challenge is, can you uh, obtain a least error with this? So when you play with the bias, just changing this green value. When you, I'm sorry, with the weight, and when you play with the bias, you're changing the value on the purple box. And every time you move something, you have some error, okay? So in the chat, can you say what is the error you get, the least error you can get? And see, you are training a model by hand, and you're playing with weights and bias, okay? So what's a good answer? Can you beat my value? Is there an optimal value? What results are you getting?
So the weight is the slope
Yes,
and the bias is the y-intercept.
the intersection, yes. And it's on the slope will be the weight in green. The bias is the purple, which is the intersection. And once you have this red line, you can predict other values. So we're trying to get a theoretical model or the line that basically we're trying to do the ordinary least square suite. Okay, so can you get less than 899 as an error? So we're trying to do it by hand. So we're trying to fit. Okay. We're trying to fit this model by hand. And well, we move one of the variables and we miss the other one and we continue playing, right? Until we get something which is acceptable, right? So it's very hard. Okay. All right. So let's continue. Um, so there are some algorithms that can help us optimize these error. So for example, we have the gradient descent method, and the gradient descent method is just for the analogy for this method is when you are up in a hill and you're trying to go into a valley, you will try to follow a path that is descending your altitude. So every time you give a step, you can always find you will always find a path which has a slope going down, right? So this is similar, but it's now automatic. So let me try to train our model doing like 100 steps at a time. Okay, my error is 680. So let me try to refine it, giving 10 steps now, 675, 671. 662, 657, 648, and my error is decreasing. And you can see here on the left, the error is decreasing, and I can continue going 10 steps at a time until I'm very close to minimizing the sum of the squares of the errors. Okay, so this is the gradient descent. This is algorithm which is doing it automatically to decrease the error until you get a very good approximate. Okay, so I'm down to 522, 518, etc. So I'm playing with the weight, which is the slope, and the bias, which is the intersection. And whatever input you have here, you will have an output. So whatever input you have here, like 1000, you will have some output. So this is the linear equation in one dimension or two-dimensional space, a one-dimensional line. Okay, and then we can think of this in a multidimensional space. So instead of a line, we're now playing with a plane, and the plane will have some slope in one direction and a slope on a different direction, and also you will have different intersection point of this XY plane in two-dimensional space. We can also start again playing with the weights and with two weights, right? And trying to minimize the error. So I go 100 steps at a time, and the error should be decreasing, right? And then 10 steps at a time. So my error right now is 1407, and the error doesn't get better than that. And you see what were the values of the slopes. Imagine you have a slope in the X direction and a slope in the Y direction and a bias. Imagine a plane on the XY axis, and in the vertical axis, which is the C direction, you have the slope. And you're playing with the intersection and you're trying to minimize the error. Okay, so that's a two-dimensional plane or surface on a three-dimensional space. Okay, and then
Carlos,
yes,
Carlos, so yeah, with the gradient descent, it's just trying something out and getting an error and then trying something else out and getting an error. So
yeah,
it's
but
just iterating, just trying, always looking for lower error,
you're
right?
going down on a hill.
Going down on a hill.
Yeah. So you're walking in a mountain. Sometimes you cannot walk directly down. You have to walk sideways and trying to continue to going down, and your purpose is just to get to the valley, the lowest point in the mountain. So that's the gradient descent method. Okay. Let me go back to the notes. And so this is an image of the gradient descent. And you have several versions of the gradient descent. So you can just follow the path, the orange path, and you're trying to descend and going from the upper part of the mountain into the lowest part of the valley. There's another method, which is the stochastic gradient descent. So every time the step is random, and is random in the direction of always trying to descend until you get into the lowest point. So there are several ways of achieving that. Okay, so now the multi-layer neural network, we have, these are the inputs, and you play with the slopes, and you're trying to get into the result of the next layer, and that's going to be the input of the next layer, and so on until you get some prediction. So this is a multi-layered neural network, has several layers. So imagine you have this will be just a surface, planar surface in multidimensional space, and you're trying to optimize that into the next stage. And the next stage will be the output of the first layer will be the input of the next layer, and so on. Okay, and so and you can go from linear to nonlinear equations, and it's going to be something similar. But at the end, sometimes you need to propagate the information not only in one direction, but also in the backward direction. So for example, when you are driving your car and you put cruise control, the cruise control will try to achieve the velocity that you have fixed on the car, but sometimes the velocity just overshoots, and then the car will try to decrease the velocity, and eventually will try to reach the target velocity you are trying to achieve. So you always need this back propagation information if you're overshooting. Okay. All right. In neural networks, there is a whole zoological of networks. So we have the perceptron, which was the first one. And then we have the feed-forward neural network. We have the radial basis. We have the deep feed-forward, and so on. So we have several ways of achieving this. And depending on what field you work, you will always find, if you're reading a paper, that people have used some specific neural network, maybe a recurrent neural network, maybe a convolutional neural network, or maybe generative adversarial network. So we have all these different geometries, how to propagate the initial information and have some input and have some output. And you can read more of every type of neural network, just opening the section here. So you will find the definition of the recurrent neural network and some graphics, or if you are following these autoencoders. So there's several types of different neural networks. You have these GANs, and you have the convolutional. These are common neural networks. And for example, convolutional neural networks are used in computer vision classifying. For example, you have the image of an elephant, and then this is the input, and the input is being transmitted into the different hidden layers, and then it will try to extract the main features of the elephant. At the end, it will try to guess what type of picture it's looking. So in this case, it's recognizing an elephant. So this is how a convolutional neural network works. Let me go back. Also, you will find a lot of transformers. For example, transformers work, for example, when we're doing some translation. So we have the input in French, comment bateau, and then the information is traveling into different encoders, and then there's a decoder, and then at the end you will find the translation. How are you in English? So this is how these transformers are used in machine translation and for Google Translate if you use it a lot. And the last part is just the large language models. You have heard about ChatGPT, the Gemini from Google, Claude from Anthropic, etc. So this is the combination of neural networks and other techniques like attention and transformers, etc. So you have some input, you have some prompt, and then at the end, you will have some answer from the large language model. So I cannot go into the detail. I'm just mentioning what there is out there. And then, so when you're talking about deep learning, you'll find all these neural networks, the convolutional, the recurrent, the generative, adversarial network, etc. And then if you are working with deep learning, then you will find there are several software libraries to work with deep learning. You may hear that people are working with Keras or TensorFlow or PyTorch or MXNet, and depending on what is your field of knowledge, people will work with one software library or the other. For example, TensorFlow was invented by Google. So if you're working in Google, probably you are working with TensorFlow and Keras. Keras is just a framework to work on TensorFlow. But then you have the other option, PyTorch. PyTorch was developed by Facebook and now it's open source. So most of the academia work with PyTorch. And then there's another framework to work with PyTorch, which is called PyTorch Lightning. And PyTorch Lightning, what it does is helps you handle all the hardware, so you don't have to be um, handling all the different parameters of your GPUs. So PyTorch Lightning will make things not technology independent, but you don't have to be worrying about handling all the hardware underneath the deep learning network. Another company is Fast AI, which is another way of working with deep learning. And then Apache has its own project called MXNet. Now it's retired. Also was developed for doing deep learning. Then there is this Cafe, which is developed by the University of California, Berkeley. And Google has JAX, which is another framework. So if you want to go into the details, you can, if you are interested in working with TensorFlow or you get across some software that is developing TensorFlow, you can learn more about TensorFlow here. You have links to the different documentations, libraries, and repo. The same thing with PyTorch. You have all the PyTorch website, and you will find a lot of neural networks, Jupyter notebooks developing PyTorch. And then PyTorch Lightning, which is more recent, is also another way of working with deep learning or fast AI, and so on. Okay, so these are the tools or the software packages or libraries to work in deep learning. Let me jump all the way down to some applications. So applications of neural networks, one is speech recognition. So you have, for example, you have maybe Alexa or Siri in your phone. You talk to the device and the device will try to translate what you're talking into instructions. Facial recognition systems, well, now it's very common in phones where you use your phone opens with your when it recognizes your face. Optical character recognition, when you're scanning some document, there is some software that recognizes the typed characters after scanning. Signature recognition can be in different modes. For example, when you're typing on your computer, every person types in a different form. So there is a field called keystroke dynamics. So every people will have a different signature the way it types. So sometimes in some online learning environments, they will ask you to in order to validate the person that you are the person who says you are, they will ask you to type some phrase, and every person will type differently, and they will take a spectrum of your keyboard dynamics, and he will try to recognize who you are. Machine translation, well, we have seen Google Translate, for example. We have also natural language generation. So there are some systems that generate phrases, text to image. Now we have all these different systems like DALI or Leonardo, where you type in some prompt and the system will generate an image out of text. Automatic summarization. You can use large language models, for example, to summarize some PDF or some different texts. So large language models can summarize some text. Behavioral analytics, I already mentioned the keyboard dynamics, and also the way people walk, it's unique. So you can sometimes recognize a friend which is far coming towards to you, and you will recognize that person because of the way he walks. Object detection, we have all these different systems. For example, when in computer vision, the camera just takes a picture and it will try to detect how many objects are in the picture. And after that, it will try to segment the image and recognize what type of object it appears in the image. Even gesture recognition. For example, Zoom recognize our hand and it will try to raise our hand in our Zoom session. So all these different applications are applications of neural networks or deep learning. And every type of problem, it's a whole field. So if you're working with computer vision, you will have to work with specific software libraries and all the different applications, for example, that have been used right now in all these autonomous vehicles or flying autonomous vehicles. They fly by themselves. They have cameras, they have software. They recognize the environment, and based on the environment, they can take decisions of going one way or another. Okay. Okay, what if you want to learn more? For example, Hugging Face. Hugging Face is similar to GitHub. In Hugging Face, it's a repository for sharing different large language models and other applications. And let me open it. It's a whole wide um, field there. For example, if you want to work with depth estimation, image classification, image segmentation, image to text, mask generation, object detection, video classification. So it's a whole new universe there where you can apply deep learning, or where deep learning is applied, and can be in computer vision. These are the fields. Can be natural language processing, can be audio, can be tabular, can be multimodal, reinforcement learning, etc. So every section here is a whole field, and you will find some software. So in the case of image classification, they have 11,000 models. For image to image, they have 300 models. Image to text, they have 466 models, etc. So it's a whole universe there of different applications. And so that's Hugging Face. And then, for example, if you are doing research, a good site to start is Papers with Code. So for example, let's say you're doing natural language processing. So you go to this site, Papers with Code, and we talk about reproducibility and open science. And so here, anything you find, you will find not only the paper, you will also find the code and some data. So in this case, it's about transformers. Um, so this is the paper you can see, and also you can see the code, and you can find all the different versions of transformers. For example, textless vision language transformer, you will find the paper, the abstract, and the code. So you don't have to start something from scratch, and you'll find some ratings from that software. Okay, so this is a very good site to start if you're doing deep learning. Go to Papers with Code, and then select whatever field you want, and then you will find the paper and the code and the data. Okay, so that's a good site to know if you're doing research, or if you're doing audio, you're doing graphs, you're doing reinforcement learning, computer vision, etc. So Papers with Code is one site to have in mind. You want to learn more, you will find different resources here from IBM, from Wolfram Research, uh, and also some cheat sheets where you want to learn about all the different glossary of terms. This person, Shervin Amidi, has good summary of different topics. So you will find information about convolutional neural networks, how they work, and all the theory behind it. And also you will find some more readings about some topics. So these are good resources to start. Okay, let me go back. Oh, sorry. Okay, so I know it's very hard in 45 minutes to know everything about deep learning, but this is just the start. Um, Next semester, you can attend our deep learning workshops, and also in the classical machine learning, we have seen several neural networks sessions. So it's just an introduction, very brief introduction to what is deep learning, and deep learning is being used in all the fields. Depending on what work, you will always find some topic and look for deep learning, and you will find what type of neural networks they're using to advance the knowledge. Okay, so that's what I have. If you have any questions, please let me know. Okay. So thank you for connecting. I'll see you next time.